Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to continue with circles and we're going to talk about secants and tangents. So let's get right to it. A secant is a line that intersects a circle at exactly 2 points. Exactly like the secant that I have right here in front of us. This line intersects at 2 points. Pretty awesome. Okay. Uh, and I'm sorry. So that's a secant, a line that intersects a circle at 2 points. Exactly. A tangent is a line that intersects a circle exactly at 1 point. So if I have a line and it intersects the circle at 1 point, it is called a tangent. Now, the intersection point of a tangent, it's called the point of tangency or the point of contact. Now, I do want to explain. Some people ask if there's a line or a segment coming from the center, is this a tangent? No, it is not a tangent. Why is it not a tangent? Well, if it's coming from the center and it hits the exterior part of the circle, that's called a radius. So a tangent line is an external line that hits or intersects the circle at 1 point exactly. And this 1 point is called a point of tangency or a point of contact. Okay? But again, the tangent is an external line. It's not internal. Okay? All right, sorry about that, guys. All right, so let's continue, my brothers. So, what is so important about this tangent? Who cares about this tangent? Well, it's actually quite important. There is an awesome postulate that states that the tangent of a circle is perpendicular to the radius of the circle it is tangent to. So what does that mean? In this particular case, we have a red tangent and we have a blue tangent, just so you could see the differences. This red tangent here, okay, has, of course, one intersection. That's called the point of tangency or the point of contact. Usually it's called the point of tangency, okay? And at this point of tangency, if I drop a radius directly to this point of tangency, I create a right angle. It's pretty awesome. If I have a point of tangency here like this blue line, okay, there's a point of tangency, and I drop a radius to this point of tangency, I have a right angle. That's the postulate. Yes, sir, my brother. Very good question. If you use this postulate on a proof, you could literally, there's no name for it. You could just say, I guess we could try to make one up, but you would just say a tangent to a circle, a radius, let's see. Yeah, a radius to the point of tangency creates a right angle. I guess you could call it the radius tangent theorem or postulate. Yeah, we could try to shorten it up. The radius tangent postulate, that works for me. As long as you understand what it means, okay? All right. So let us continue here. Secant and tangent segments. Okay. When you have a tangent segment, it's the same as a regular tangent, except it's an external segment. But instead of it being a line that continues forever, gentlemen, it literally is a tangent. And it ends. There's 2 endpoints. Same postulate, though. If I go ahead and drop a radius to the point of tangency, it creates a right triangle. A right angle, sorry, not triangle. Okay? Same exact theorem. Now, sometimes I have a segment that is longer, and it actually goes to the circle, creates one point of tangency. In this particular case, I have two tangents. I have this tangent segment, and I have this tangent segment. Some people may say, but why isn't that just one tangent? If it was a line, it would just be one tangent line. But if you see a segment that intersects the circle at one point of tangency, you have two separate tangent segments that combine. Okay? Very important later on for proofs. A secant segment. Remember how we were saying that the point of tangency or a tangent line is external. If you have a secant segment, okay, it's the same thing as a regular secant, except it's a segment that intersects the circle still at exactly 2 points. The whole entire segment is called a secant segment. The external part, literally, is called the external part. Okay? This may seem very kind of stupid, guys, but it's very, very important that you know the nuances of this. There are differences. All right. Two-tangent theorem. Very cool theorem. Two-tangent theorem states that if two tangent segments are drawn to a circle from an external point, then those segments are congruent. So you have this external point out here, and I draw a tangent segment from that external point to the same circle. These two tangent segments are congruent. And I'm going to give you another little tidbit of information. This is going to come later on, but you know how sometimes I like to go ahead. Remember that BC has an arc measure, correct? And as you can see, this angle is angle BAC, correct? Right? Let me show you something pretty cool. Arc AB plus angle BAC will always equal 180 degrees. I promise. Pretty cool. So again, if you have an external point and you have two tangents from that external point, that creates two congruent tangent segments. And just for giggles, arc CB, why did I put AB? Because I'm not paying attention. Arc CB plus angle BAC will always equal 180 degrees. I promise. Okay? Not too bad, right? So far? May I continue, boys? Yeah? Okay. Thank you, my brother. Now, tangent circles. By now, hopefully you've realized tangent means that they're intersecting at 1 point. Secant at 2 points. Tangent circles are circles that intersect each other at exactly 1 point. At exactly 1 point. Tangent circles are circles that intersect each other at exactly 1 point. Now, there are two types of tangent circles. You have external tangent circles and internal tangent circles. From the drawings here, it's pretty self-explanatory, but you know that I like to explain things all the way. An external tangent, okay, it means that the circles are externally tangent if each of the tangent circles lie outside the other. So this point of tangency here, which is C, is on the outside of both of these circles. Okay, so I have this point of tangency but it's on the external of both circles. An internal tangent, if you think about that, look at the figure here. The circles are internally tangent if one of the tangent circles lies inside the other. Please notice that the actual tangent line is still outside of both circles. But when I have one circle within another circle and they intersect at one point, those are two tangent circles, but those are internal tangents. So external tangents, the circles are both outside of each other, okay? Internal tangents, you have one circle inside of another circle. So you have external tangent and internal tangent. Yes, sir? You got a question, Bob? Oh, okay, I'm sorry. I thought you had a question. Now, why is this important? Word problems. In word problems, they'll tell you two circles are externally tangent. You know that you're talking about two circles that intersect like that. If I say two circles are internally tangent, that means that you have two circles that intersect like that. So very important nuances for word problems. Does that make sense, boys? See some of you writing, which is cool. You got it, my brothers? Okay. Now, common tangents. If you see these two circles here, excuse me, you have two common tangents here. First of all, PQ is the line of centers, it's called. When you have the center of circle P and the center of circle Q, and you draw a line that connects these two centers, it is literally called the line of centers. Pretty straightforward. Now, if you look at XY, XY is called a common internal tangent. Why is it internal? It's an internal tangent because it's going in between both circles. Hopefully by now you've realized, guys, that most things in geometry are pretty logical based on the figure. So a common internal tangent is called internal, again, because it's going in between both circles. And then you have what's called an common external tangent. And of course, by the figure here, an common external tangent is a tangent to both circles, but it's on the outside of both. So if the tangent is going in between both, it is internal. If the tangent is on the exterior of both, it is called a common external tangent. And the line that connects the centers is called the line of centers. This makes sense so far? Okay? So let's get right to it. Given that XY is a common internal tangent, please think about that. It's internal, why? Because it's in between, okay? I'm sorry, I lost my train of thought. XY is a common internal tangent to circle P and circle Q. X and Y, at X and Y, that means that those X and Y are the points of tangency or the points of contact. XS is tangent to circle P. So XS is tangent to circle P. It is a tangent segment. It intersects only at one point on the circle. And YT is tangent to circle Q at t. So yt is tangent to circle q at t. I want to prove that xs is congruent to yt. So, my brother. No, yt is not a tangent to circle P. And that's a wonderful question. I'll tell you why. If I were to extend this segment, wouldn't it intersect at two spots of circle P? So that would become a secant. Very good, my brother. Yes, sir. No, yt would not be congruent to, wait, what did you ask? Yes, yt is congruent to xy because of the two tangent theorem, and xs is congruent to xy because of the two tangent theorem. But why or how is xs congruent to yt? You guys just proved it. I'm so proud of you. I am so freaking proud of you guys. You guys nailed it. That's a long given, so we already described the givens. Again, just a visual. xy is an internal tangent to P and Q. xs is a tangent to circle P, and yt is tangent to circle Q. So now, you guys literally took the wind right out of my sails. Now I can't look cool. xs is congruent to xy because of the two tangent theorem. xs is congruent to xy. Wow, guys, I'm really, really proud of you. xy is congruent to yt because of the two tangent theorem. But wait a second. What's that? xy is common here, correct? So that means that xs and yt are congruent because of the transitive property. That was awesome. And seriously, guys, that may seem like nothing, but that makes life so much easier when we're calculating things, which is what we're going to see now in the next few examples. On the SAT, they love to give you stuff like this and then calculate. Like they'll give you a value for xs, and then they'll say find xt, or xy, rather. Well, if you know the two tangent theorem, you're going to answer that question in about 5 seconds. If you don't know that theorem, you're just going to sit there and wonder, what do they want? How do we get that? And then you start wasting time. Does that make sense, boys? All right. Number 2, radius. You guys are awesome. The radius of this particular circle is 8 millimeters. The tangent segment is 6 millimeters. Find OP. Okay, all of you are saying 10, but what really makes this 10? Why are we allowed to use a Pythagorean triple, sir? Very good. Remember, my brother, you were asking, who cares that the fact that the radius is perpendicular to a tangent? Who cares about that? Well, we do. Because this radius was dropped down to the point of tangency, I can now use my postulate that that is a right triangle. Yes, sir, my brother. Correct. So it's a 3, 4, 5 triangle times 2, and that's why OP would be 10 millimeters. Now, of course, if you don't know your Pythagorean triples, or if it's not a Pythagorean triple, you simply use your Pythagorean theorem, a squared plus b squared equals c squared. Does that make sense? So OP would be 10 millimeters. And again, very difficult if you could not use that, what do we call it? The tangent radius postulate. This would actually be quite impossible. Because if that's not a right triangle, we could not use the Pythagorean theorem. We would not be able to use the Pythagorean triples. So it's very important that we know that postulate. Does that make sense? Okay. A circle with a radius of 8 millimeters is externally tangent to a circle with a radius of 18 millimeters. Find the length of the common external tangent. So what I'm trying to find here is AB. I want to find the length of AB. Whenever you're given a problem like this, guys, there is a procedure that you always want to follow. So let's go through the procedure. First of all, draw the segment joining the centers. Okay? So we're going to literally, hold on, this should be a little bit longer here. Sorry. So what we're going to do is we're going to draw the line of centers. That's step one. Done. Step two, draw the radii to the points of contact. I already drew them for you, but you would draw QA and you would draw QB. Or PB, sorry, PB. Number three, draw a line parallel to the common tangent through the center of the smaller circle. So what are we going to do there? What does that mean? To the best of our ability, guys, we're going to draw a line that goes from the smaller circle's radius, very important, and we're going to go ahead and draw it to some point on the radii of the larger circle. Since it's parallel, gentlemen, please pay attention to what forms here. This is 90 degrees because of the tangent radius theorem. This is 90 degrees because of the tangent radius theorem. These two guys are parallel. What did I just form? Not a parallelogram, but a rectangle. Notice that this line will intersect the radius of the larger circle to form a rectangle and a right triangle. If it's a rectangle, doesn't that mean that this is 90 as well? So that means that this is 90 as well. So that means that I created a right triangle right here. Is everyone with me so far, my brothers? Promise? Okay. They had told us that the larger circle had a radius of 18, correct? They had told us that the smaller circle had a radius of 8, correct? You with me here, guys? So, pay attention. Number 5. Use the Pythagorean theorem and properties of the rectangle now to solve exactly what it is that we are looking for. Okay, you ready? I'm going to blow you away now. If PB is 8, that means that this segment here, bless you, is 8, correct? So even though it doesn't look it, what is this little segment here? 10. But if the radius of the large circle here is 18, and the radius of the small circle here is 8, what is QP? 26, guys. Isn't that the hypotenuse of the blue right triangle that I created? So what is the length of this segment right here? It's a 5, 12, 13 triangle, guys, times 2. So this is 24. If it's a rectangle, aren't opposite sides congruent? So what would AB be? AB would also equal 24. The beauty of this is that it's the same procedure over and over when they give you this kind of a problem. This is a very popular kind of problem, again, on the SAT and the ACT as well. Yes, sir. Yes, sir. Of course I can scroll down. Did you have a question, my brother? No worries, man. Thank you. Now again, just because I want to make sure you understand this, I want to go through it one more time. So you're given the information basically that you have two circles and you have a common external tangent. So here's my common external tangent. You draw your radii, you can label it. You draw your radii, you can label it. You draw the line of centers. Now you draw a line from the small circle to the radii of the big circle, which is parallel to the common tangent. That's 90 because of tangent radius theorem postulate. That's 90 because of tangent radius theorem. If that is parallel and these two angles are congruent, that means that this is a rectangle. So that's a 90. This is a 90. And now I have created not only a rectangle, but a right triangle. If the small side or the small radii is 8, that means this is 8, and this guy here is 10. The radii of the large circle is 18. The radii of the small circle is 8. So that means this side is 26. I have created now a 5, 12, 13 triangle times 2. So that means that this side here is 24. Opposite sides are congruent, so AB would be 24. Does that make sense, boys? We got plenty of time, so I want to make sure you guys got this. Okay. May I continue? Thank you, boys. All right. Last but not least, dog. It's called the walk-around problem. They tell you that segment AB is 10. Okay. Cool beans. They tell you that segment BC is 15. Okay. That sounds good enough to me. They tell you that AD is 18. Okay, cool. And they want to know, what is CD? All right. Give me 1 second. Let me do something here. I wanted to, let me see if this is, yeah, I messed up. Hold on. Give me 1 second, please. Really? Oh my God, you're wrong. It was a horrible guess. All right, guys, remember, boys, come on. We can't guess on things, not in geometry. So that guess of a 7 was absolutely wrong. We cannot guess. They had told us that AB is 10, BC is 15, and AD is 18. I want to know what this is. Okay. Remember how I talked to you guys about that tangent segment that really breaks up into two different tangent segments? Well, this circle is surrounded by them, okay? You have a point of tangency here, 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 and here. Now, pay attention to this. We've gone over this before, but I want to really take my time with this and make sure you understand the concept here. If the whole entire BC is 15, bear with me here. Do we know the length of B to this point of tangency? Okay, you're saying 7.5. Who said that that's the midpoint, guys? You don't know that. So do we know this? Again, do we know the length of B to this point of tangency? So what can we call that? X. Now, pay attention. If that's X and the whole thing is 15, what is this point of tangency to C? 15 minus X. Beautiful. Now check it out, guys. Isn't this a two-tangent theorem? So what is C to this point of tangency? 15 minus X. Are you with me here? Okay. Now, if from the point of tangency to B, that's X, what would B to this point of tangency be? X. But AB is 10, so what would A to this point of tangency be? 10 minus X, you guys rule. If that's 10 minus X, Two tangent theorem. What is this right here, my brothers? 10 minus x. And then, if this whole entire AD is 18, oh, wait a second, did I mess up here? No. What would this point of tangency to D be if the whole thing is 18? Thank you. 18 minus 10 minus x. You feel me here? You with me, guys? So two tangent theorem, what would D to this point of tangency be? 18 minus 10 minus x. Does that make sense so far? Kind of? Talk to me. That's why I'm teaching, guys. Promise? Okay, now, you may be saying, okay, that's really pretty, Moral. That's awesome. So what? Doesn't 15 minus x plus 18 minus 10 minus x equal CD? Calculate it, brothers. 15 plus 18 is 33. Negative x minus 10 plus x, the x is cancel. 33 minus 10 is 23. And guess what, my brothers? CD is 23. Sir, the question was, why would the x's cancel? Thank you, my brother. Doesn't this negative distribute to both, Papa? Yes? Does that make sense? All right, guys. You rule. Thank you very much. Sorry about my voice. I'm a little sick. Hope you learned a lot. God bless you, and have a wonderful day. Bye-bye.